Part 3 of Chapter 14, the Autonomic Nervous System, in our Human Anatomy and Physiology text. In Part 2, we learned about the organ-by-organ functions of the parasympathetic and sympathetic nervous systems. And now in Part 3, we're going to take a look at the specific cholinergic and adrenergic receptors found on various effector organs. So, acetylcholine is released by cholinergic fibers. That's the term used to describe a neuron which secretes acetylcholine. And adrenergic fibers release norepinephrine. So cholinergic fibers are part and parcel of the parasympathetic postganglionic neurons, and the postganglionic sympathetic neurons are adrenergic receptors, as we discussed in the past. So now let's look and see some specific receptor types for acetylcholine and norepinephrine. So here's just to remind you, this is the schematic diagram we used right at the beginning. Norepinephrine is the neurotransmitter of the postganglionic sympathetic neurons, and the postganglionic parasympathetic neurons release acetylcholine. Note, though, that in the ganglia of both divisions, acetylcholine is the neurotransmitter, and we'll see that there's a different receptor type there than on the effector organs of the parasympathetic division. So, starting out with the cholinergic receptors, there are two types, two different genes that produce a receptor, a membrane receptor for acetylcholine: nicotinic receptors and muscarinic receptors. Nicotinic receptors are found in the neuromuscular junctions of skeletal muscles, as well as on the postganglionic neuron cell bodies in the ganglia. So, when we go back to that drawing and look, these postganglionic neurons have nicotinic receptors on their cell bodies in both sympathetic and parasympathetic ganglia. Muscarinic receptors are found on the effector organs of the parasympathetic nervous system. So if you consume some muscarinin, a toxin from certain family of mushrooms, it'll activate all the parasympathetic target organs and produce all the expected effects that we talked about last time. Massive salivation, overactivity of the muscles, smooth muscle of the digestive tract, may cause vomiting or diarrhea, and salivation that'll slow the heart down to a crawl heart rate. So all kinds of sympathetic effects will be caused by muscarine. Adrenergic receptors include two families described by Greek letters alpha and beta. I shouldn't say two families. Two different Greek letters are used to name these receptor types because there are alpha-1 receptors on one target organ type or group of organs. There are alpha-2 receptors, that's a different gene on different cell types. And then 3 types of beta receptors. All of these are norepinephrine receptors and also bind epinephrine. So, let's take a look and see what the functions are. Alpha-1 receptors are found on vascular smooth muscle. So we said there's sympathetic tone to the blood vessels that causes vasoconstriction and maintains your blood pressure. And it's through alpha-1 receptors. So that's where we would find those receptors. Beta-2 receptors are found on the smooth muscle of your airways in your lungs. So when norepinephrine or epinephrine bind there, it causes bronchodilation, relaxation. Let's look at just a little bit more complete list of adrenergic receptors and their functions. So beta-1 receptors for norepinephrine and epinephrine are found on the heart and increase the heart rate. Increases heart rate and force of contraction, and also, this is important, on the kidneys, causing them to release renin. And renin will induce some changes that will raise the blood volume and blood pressure. Beta-2 receptors are found on the airway smooth muscles and causes bronchodilation. Whoops, where are we? Bronchodilation is what I'm looking for. Dilation of bronchioles. Okay, there we go. It turns out that beta-2 receptors are also found on blood vessels and skeletal muscles, which explains why activation of the sympathetic nervous system does not constrict the blood vessels in muscles so much, so that they can auto-regulate, they can control their own blood flow during exercise. The main thing to remember is beta-2 bronchioles, the airways of your lungs, will dilate when activated. Beta-3 receptors are found in adipose tissue, and when epinephrine and norepinephrine come along, they'll cause release of fatty acids into the blood. Right? Sympathetic nervous system mobilizes fuels for exercise, for muscle metabolism, and lipolysis, lipid lysis, breaking down fat in the fat cells, causes the release of fatty acids into the blood for use as a fuel. Alpha-1, as we said, alpha-1 receptors are found on the vascular smooth muscle and causes vasoconstriction. Also, it's responsible for dilation of the pupils of the eyes by the parasympathetic nervous system. Sorry about the background. We have two new birds, and they're very, very vocal today for some reason. So that's the main. Actually, alpha-2 receptors are found on adrenergic axons, so that it will actually inhibit the release of norepinephrine from those neurons in certain cases. But the main ones to know are beta-1, heart and kidneys, beta-2, airway smooth muscle, beta-3, adipose tissue, alpha-1, vascular smooth muscle. And we also have already named the location of the nicotinic and muscarinic receptors. Let's look at some specific important drugs. I mentioned at the beginning of this chapter that one of the reasons this chapter is so important and studying these systems is so important is that a large part of clinical medicine involves manipulating these receptors we just talked about, either activating or inhibiting these various types of autonomic receptors to control organ function. So let's take an example. What about a drug that activates muscarinic receptors, acetylcholine receptors on the effector organs? When you have a drug that does the same thing as an autonomic neurotransmitter, the word mimetic is used, meaning it mimics the function. So a parasympathetic is a drug that acts like acetylcholine, so we're going to see where we might use a drug to activate a muscarinic receptor. When people have glaucoma, they have too much pressure in their eyes, too much volume of fluid in the eyeballs, and so if we use eye drops of pilocarpine, that's a parasympathomimetic that will cause the release of some of that fluid from your eyeballs out into the venous circulation. We're recycling the fluid in your eyes faster and the pressure goes down. That pressure can damage your retinas. Let's see some more examples. What about a way of activating the muscarinic receptors indirectly? Acetylcholine esterase inhibitors. We're going to block the breakdown of acetylcholine in the synapses, and so prolong its presence and increase its activity. And we said that myasthenia gravis is a disease in which there's not enough acetylcholine receptors in the neuromuscular junction. Well, pyridostigmine or neostigmine are drugs that are used to elevate the amount of acetylcholine remaining in those synapses so that the few receptors that are left will be surely bound by acetylcholine. So people with myasthenia gravis may be treated with drugs to block acetylcholine esterase. We also mentioned that there are acetylcholine esterase inhibitors that are used as biowarfare agents. They're also used as insecticides. Sarin is a chemical that's used as a chemical warfare agent. Organophosphate insecticides are also cholinesterase inhibitors. In your bottle, in your can of Raid, you'll see those ingredients listed. How about a sympathomimetic? Sympathomimetics include albuterol, which is used in inhalers to counteract the effects of histamine causing bronchoconstriction. When someone has an inflammatory response in their lungs, either asthma or an allergic response that's causing bronchoconstriction and they can't breathe, we can give them some albuterol if it's not too severe. And albuterol will bind to beta-2 receptors and cause bronchodilation. If it's a severe case where someone is actually in danger of dying from an allergic response, then we might use an epinephrine syringe, an EpiPen, stab that into the thigh muscle and get some epinephrine into the blood and do the same thing to bronchodilate quickly in order to save that person. But in more mild cases, albuterol is used as a very commonly used drug to bronchodilate. It's a sympathomimetic. Pseudoephedrine is used in nasal decongestants, either orally but oftentimes just sprayed right into the nasal cavity. And pseudoephedrine activates alpha-1 receptors in the mucosa, and that causes the vasoconstriction, causes less of the fluid to be produced as secretions, and the tissue shrinks, and the amount of mucus is greatly decreased. So your runny nose is ameliorated, and you can breathe through your nose again. So there's a bunch of different like compounds that cause alpha-1 activation. A sympatholytic, the opposite term, a drug that inhibits a receptor for an autonomic agent is called a lytic drug. A sympatholytic is one that inhibits a particular class or family of adrenergic receptors. Metoprolol is probably the most popularly used beta blocker. I'm sure you've heard of beta blockers. It's a lazy term because what we really mean is beta-1 blockers. And so metoprolol is used to lower the heart rate, lower the work of the heart. It's not going to contract as violently, to lower the blood pressure. That's one of the applications. So metoprolol may be used for people with hypertension, and we haven't had success in other ways of lowering the blood pressure down. It's also used to suppress arrhythmias. It stabilizes the heart cycles. So that's another example of an important drug used that's a sympatholytic in this case, manipulating the autonomic receptors for medical purposes. Most of the organs that are innervated by the parasympathetic and sympathetic nervous system exhibit antagonism. One division does one thing to an organ, the other division does the opposite. Dual innervation is called, and again, these are usually antagonistic effects. The sympathetic nervous system generally predominates. In other words, if you have norepinephrine, epinephrine present, and also acetylcholine, we'll see the sympathetic response. So, for example, what's an example of the antagonistic interaction? Parasympathetic nervous system lowers the heart rate, sympathetic nervous system increases the heart rate. Acetylcholine causes bronchoconstriction, epinephrine and norepinephrine cause bronchodilation. So just some examples, but go through your list that we looked at in part 2 and you'll see that they're just almost entirely antagonistic effects. And there's a couple of examples where there is autonomic tone. You should be aware of that. This slide is just bringing that to the fore because I want you to remember that. Where's an example where there's sympathetic tone? Well, the vascular smooth muscle. Blood vessels, the sympathetic neurons to your blood vessels are always releasing norepinephrine. We can either turn up that epinephrine output and raise the blood pressure, or we can lower the amount of epinephrine, the amount of sympathetic activity, and lower the blood pressure. So that's an important way that the blood pressure is maintained in the short term. Also, during exercise, we can elevate the sympathetic tone to some blood vessels, certain organs, such as the digestive tract, and then all the extra blood that would have gone through those organs will be diverted over to the exercising muscles. So the sympathetic nervous system is the only division that innervates the blood vessels, and it has sympathetic tone. Parasympathetic tone, we already mentioned, is present in the heart. So parasympathetic neurons are always releasing acetylcholine onto the heart at rest, and that's what controls your resting heart rate. The native pacing rate of your heart would be considerably faster, 25 beats per minute or so faster than your resting heart rate actually is. And if you look into the reason for that, it's because of parasympathetic tone. Another example of where there are only sympathetic fibers, I lost track, is the adrenal medulla. The adrenal gland is only innervated by sympathetic neurons. I know it's not mentioned on this slide, but I just wanted to bring that up while we're on the subject. Cooperative effects between the divisions, we already mentioned that parasympathetic nervous system causes erection of the penis and clitoris, and then sympathetic fibers are responsible for ejaculation and vaginal peristalsis during orgasm. So we have two systems, two divisions working together in that important example of reproductive function. Another unique role of sympathetic division, the sweat glands. Sweat glands are innervated only by sympathetic neurons. The hypothalamus uses those neurons discretely. It's not the same as the diffuse response you get during exercise when the adrenal medulla releases epinephrine and norepinephrine. When it comes to thermal regulation, the hypothalamus can activate individual or groups of norepinephrine-releasing neurons onto sweat glands to get that evaporative heat loss going. When you exercise or activate the sympathetic nervous system, the kidneys release renin, and renin activates a process that will increase the blood volume and blood pressure. It's an enzyme released into the blood by kidneys to elevate blood volume and blood pressure. So that's an important function, exercise-related function of the sympathetic nervous system on the kidneys. Epinephrine and norepinephrine also increase the metabolic rate of cells in your body, and that's an important function when you're exercising. Just everything gets cranked up, producing more ATP, producing more heat, and so forth. So the more epinephrine that's circulating and the more norepinephrine, the greater the metabolic activity of your body. It provides the fuels for exercise, of course, and it increases the metabolic rate of the cells. Interestingly, we've already talked quite a bit and just reviewed the fact that acetylcholinesterase in cholinergic synapses destroys acetylcholine when we're done stimulating those synapses, and that's how we terminate the effect of those synapses. Well, sympathetic nervous system, because of the diffuse response, once you crank up the sympathetic nervous system during exercise or during basic activation of the nervous system, those hormones are going to circulate for upwards of 30 minutes because they have to be removed from the circulation by the liver. And so it takes a considerable period of time to remove all of those catecholamines, they're called, from the circulation so that all the sympathetic effects can settle down back to resting levels. So it's much slower turning off the sympathetic division than the parasympathetic division. Join me next time and we'll look at just a few more aspects of the autonomic nervous system, and we'll finish up this chapter.